Hello friends, so in this video we will see Maxwell's equation and some related problems. Uh, Maxwell's equation means it's a simple point form equations of divergence and curl of the field. Divergence and curl of vector fields. For example, here there are two vector fields that we talk about, electricity and magnetism. Divergence of electricity, which is this, and divergence of magnetic field, curl of electric field, curl of magnetic field. So these four equations we will see. This is the left hand side, we will see what is the right hand side. We will start with del cross E for electrostatics case. See, always remember here there are three different situations, that is the experimental situations: magnetostatics, electrostatics and electromagnetism. For example, we start with electrostatics. In electrostatics, what is del cross E? Let us look at a situation like this, that is when there is a charge is at rest, and to get del cross E, moreover there is one more thing. Whenever you are interested in the curl, we will borrow a mathematical theorem called Stokes theorem. The Stokes theorem says something like this. If you have something like this, E dot dl, it can be written like this: an open surface del cross E dot ds. So here, to get this equation, looking at the curl, the Stokes theorem says that if you want this, try to get an equation like this. How do you get an equation like this? Closed loop, walking in a closed loop path. And if you walk in a closed loop path like this, what is the total work done? Because we know that whenever you say E dot dl, that is a field dot dl, it is the potential, whether it is gravitational field or electrostatic field. Field dot dl, that is the work done is work done potential energy, means it is force dot dl. But if you are interested in the potential, just a potential, that is the potential energy divided by the charge, then it is field dot dl, integral field dot dl. Say for example, if you take a unit positive charge and if you walk like this, then that means you are walking against a plus charge, both are plus, so rippling force, you are walking like this. So you have to spend energy, system has to spend some energy, that is this, system has to spend some energy. And if you walk like this, considering this equipotential surface means the surface where the potential is same. Whenever the potential is same, work done is 0. So that means here total work done will be 0. Here rippling force, you are going away from it, so you will gain some work. Here it is again 0, equipotential surface, so the total work done is 0. Since the total work done is 0, I see that the left hand side is 0, so the right hand side should also be 0. So the del cross E for electrostatics is 0. We will come back to the same thing in electromagnetism, where we will get non-zero. Anyways, here del cross E is 0. That means the electric field here is mathematically, they say it is conservative. Conservative means irrespective of the path of integration, the work done is same, irrespective of path of integration. I'll just give you an idea of what it means. For example, if you have this one problem, charge q here, and if you take a distance of 1 meter here, and here also 1 meter, if you move from here to here, see in these two places, the work potential will be same. Potential at this point V1, potential at this point V2 will be same, because they are the same distance from the charge, right? So work done in moving a charge from infinite distance to all the way infinite distance to here, or all the way infinite distance to here, will be the same. So the potentials will be same because they have equal distance. If you have to move a charge q, small q, from here to here, then the total work done will be 0. Why? Because they both are at the same potentials. Either you move like this or you move like this in equipotential surface, or you move all the way like this, it will be the same. Irrespective of the path of integration, the potential will be 0. Irrespective of the potential will be same. We should say potential will be same. But in this particular example, it will be 0 because they are both are the same potential. So it means that you are moving along the equipotential surface. So the work done is 0. I'll take another example. For example, if you have a circuit like this, say that is a resistance here. You would have seen this example many times before. If you have a current flowing like this, say for example 1 amp is flowing, the current measured through this path, or you measure the potential measured through this path, or you measure the potential through this path, the total potential or the work done will be same. Why it is same? Irrespective of the path of integration, work done is same. We say voltage across junctions are same because here the electric field is non-conservative. Okay friends, I started with Maxwell's equation. Maxwell's equation means it is a set of equations which will talk about divergence and curl of a field. Two fields here, electric field and magnetic field. For curl, we are interested in using, we borrowed a theorem called Stokes' theorem from mathematics. That's an easy way to get a divergence, curl equations. And for electrostatics, it ended up like this. Now, the next will be, I'll try to do the same thing for magnetostatics. Magnetostatics, we are interested in the curl. For the curl, we have to use Stokes' theorem. So what I will do, I will go to the, if you remember, we had something like this. That is this Ampere's law. In Ampere's law, we had something like this, H dot dl equal to current enclosed, we said. So here again I will apply Stokes' theorem. So it will be H del cross H dot ds. So I will have to write right side equation also something like that. So I will try to write I. For example, if you zoom into the current carrying conductor, if you say the current carrying conductor is zoomed in like this, and say there is a small areas here, ds. If you try to split it into small areas, if you say that this current coming through this is total current divided by the area, because it's the smallest infinitesimal area, right? So this one we call it current density I. So you can say I is J current density into area, or you can say double integral J dot ds. So right side equal to left side, I will end up getting del cross H equal to G. Curl of a magnetostatics case. We started with Ampere's law. We said that the current I can be written as current density. Current density means total current divided by area, right? So you can write it like this. Total current is current density into area. Area is double integral ds. So we ended up getting J like this. Actually, this J was corrected to be Jc plus Jd. Jc means it is the current through the conductive material. We call it sigma E. Jd means it is the current through the capacitance or dielectric medium. We say it is rate of change of flux density, electric flux density. So it goes like this. Anyways, this is the equation curl of the magnetic field. Next, we will talk about electromagnetism case. In electromagnetism case, we are interested in curl again. We will go to the only law there, Faraday's law. Lenz's law will only give the direction of the current. So Faraday's law says V equal to d phi by dt. It's also equal to closed loop integral of E dot dl. Here we will try to use Stokes' theorem. D del cross E dot ds. This d phi by dt, for example, if n is there, n number of turns, so this equation will turn out to be n phi can be written as B into A if you remember, B into A. So I will try to write this area is double integral ds. So it will turn out to be n double integral ds. This is for the area. And what will happen to the dou v by dou t. So this is the equation. If you equate the left equal to right, you end up getting del cross E is minus dou v by dou t. This is the final equation for curl of the electromagnetism case. So we started with this one, that is this curl of electrostatics. It is 0, that is the electric field is conservative, we said. Here the curl of magnetic field is non-zero, so the magnetic field is non-conservative. Non-conservative means depending on the path of integration, the total work done is different. For example, here we said that you walk in a closed loop fashion, the total work done is 0. We said if you walk in a closed loop fashion, total work done is 0. But we all know that if you have a current carrying conductor, if you walk in a closed loop fashion, it's not a 0, it is magnetic field. You are getting some magnetic field. Magnetic field into 2 pi r in the path. For example, if you are walking multiple times, then you are going to get n times. If you walk n times in a loop, then you will get not 0 but n times of that value. So depending on the path of integration, you will get different values. That is, if the radius of this path is more, then you are going to get bigger value. Next is electromagnetism. Again here also electric field is non-conservative. Electric field is non-conservative. For example, if you have a circuit like this, say the same circuit, I just remove the DC source, 1 ohms and 9 ohms, and say for example we try to make it electromagnetic case. How do you make it electromagnetic case? The rate of change of magnetic flux should be there. So I try to bring a pole like this closer to this, perpendicular to this. So as you bring it closer, there will be some current induced. For example, if the current induced is like this, 1 amps. Current entering here plus, current leaving here minus, current entering here plus, current leaving minus. The potential here, if you try to measure through this path, you are going to get minus 1 volts. If you measure it through this path, you are going to get plus 9. So depending on the path of integration, you will get different potentials. So we say here it is electric field is non-conservative because depending on the path of integration, you will get different potentials. This is about the curl. Next is we will talk about divergence. Divergence, we will start with electrostatics case. Electrostatics case means the charges are at rest. For example, there are some charges like this, and you enclose this with a big bedspread like this, cover it with that. And if you say that charge is, if you remember Gauss law, we were saying that charge is flux. If that is so, the understanding goes like that. Then what is the total flux coming out of this big enclosed bed sheet? It will be 4 coulombs. For example, if you draw one line for 1 coulomb, the electric field lines are imaginary drawn by us. If I try to choose to draw one line for 1 coulomb, I am going to get 4 lines because there are 4 coulombs of charge. I just presumed it like that. Then what can you do about it? Whenever you use divergence, you will have to borrow this divergence theorem from mathematics, which says a closed loop d dot ds will lead to volume integral del dot d into d volume, dx dy dz. That's what I mean by d volume. So here you are going to get q psi is the total flux coming out of the surface, right? For example, if you divide this into small ds surfaces, in each surface, how much flux is coming out is d. D is the flux density, right? So the total number of flux coming out divided by area. So area divided by area means small area ds. So total flux coming out of the small area. So this can be written as closed loop d dot ds. And the same way you can write this. Say if you take small volume, take a small volume, the total charge inside a volume is small. If you distribute this into many volumes, for example, if you cut this total charge distributed in space into small volumes, dV1, dV2 like that, in each volume the charge available is called rho v, then the total charge Q will be rho v1, rho v2 like that. You just have to keep adding it, or you can say that it is rho v ds, dv, dx dy dz. So this is Q. Now what have you got? We have got a left hand side like this, d dot ds, and the right hand side like this. I try to borrow this divergence theorem, then the left hand side will become del dot d, dv, right hand side will become rho v. So del dot d is, or otherwise you can say d is charge divided by 4 pi r square. So charge will be area, right? You all know that electric field is charge divided by 4 pi epsilon r. So the relation between these two is d epsilon. So del dot d is rho v by epsilon. So now, if you remember in one of the problems, we were saying that 1 by differentiation. Why do I write 1 by differentiation? This is a differentiation parameter. So 1 by differentiation is integral. If you remember one of the problems, we were talking about relation between a charge distribution was given for a diode, and we were interested in knowing what is the electric field for it. To get the electric field pattern, we had a charge profile like this. For the charge profile, what will be the electric field? Electric field will be like this. Why is it becoming like that? When you integrate a step, it becomes a ramp. Alright, this is about the divergence theorem for the what is called electrostatics. How about magnetic field? Divergence for magnetic field. Divergence for the magnetic field will be divergence means it talks about source or sink in the given region. See, a practical understanding of divergence is it talks about source or sink in the given region. For example, in the electric world, we had only plus charges. When you have only plus charges, we got some non-zero value. Imagine you have same amount of plus and same amount of minus. If you enclose this with a surface, what is the total flux coming out of it? Zero. Total flux coming out of it is zero. So in that case, the divergence will be zero. For the electric world I am talking about, divergence will be zero. So depending on what is the flux, net to flux coming out only, divergence will give answer. If there is no net flux coming out, divergence will be always zero. But for the magnetic field, we all know that for a magnetic field, magnetic field line will always start and end at the same point, or otherwise we can say you cannot have a magnetic monopole. You cannot separate a north pole like this. It will always come with the north and south, and the magnetic field lines always start and end at the same point. This is how a magnetic field line. So since it will be always like this, if you try to enclose any kind of Gaussian surface, you will see the net flux will always be zero. Whatever leaves, that will enter. So the net magnetic flux will be net magnetic flux. The word net is very important. Net magnetic flux will always be zero. If the net magnetic flux is zero, divergence is also zero, because divergence talks about Remember, divergence talks about source or sink in the given region. If there is no source, no sink, whatever leaves that enters, then the net magnetic flux is 0, then the divergence is always 0. This is always. Okay friends, so we ended up with these things. So what is the equation here? For electrostatics case, it can be 0. But for electromagnetics case, it is like this. And here we got some value. And here it will be JC plus JD we said. And here it is always 0. This is Maxwell's equation. Thank you.